Good evening, everyone. In last class we have started design of the transformer. In design of the transformer, in last class we have seen what are the different what are the different things that we require to design a transformer. And first of all, we see what is the different type of transformer. And in this, we've seen that the main type of the transformer is a core type and cell type. And in this core type and cell type, we see that how they have been different from each other and how we can arrange to them for the transformer purposes. It's how a binding will be arranged in this for the transformer purposes. Once we completed this, then we see what are the different components we required for the designing of any transformer. And in these components, we have seen different type of things, that different requirement. These different requirements was the what is the number of turns and all these things. So we continue this discussion tomorrow today as well and see how transformer are basically designed. So let's start this. So in this we have seen that what are the different nomenclature is there. So in this nomenclature, we have seen that VP and VS is at a terminal voltage of the primary and secondary. IP and IS is the primary and secondary current per phase. TP and TS is the number of turns on the primary and secondary side. EP and ES is the EMF induced in the primary and secondary side. Then we have a ET per turn means how many turn it is the EMF that will be induced per turn into the system. Uh, Similarly, we have other parameters as well, like K, delta, uh, area, AI. These are some parameters that we have gone through yesterday, and we have seen that how they are required for the designing of any transformer. So before designing any transformer, what we understand that the the rating of the transformer is most important. Based upon the rating only of the transformer, or based upon the kVA and the voltage rating of the transformer, we can decide that how this transformer will be decided whether it is a port type or the cell type. What is its purpose? Whether it is a uh, power transformer or distribution transformer, because both transformer has a different use. So and for which voltage or which phase we require, whether it is a three phase or the single phase. So depending upon all these things, we will understand that how big the transformer will be, how many tons we will require, and if you understand the terms, then you will understand how bulky it will be. So based upon that, we can decide how what physical size of this transformer will be. What will be the window? How big its area, cross sectional area will be. These all things will be decided based upon the its rating and all these things. So already we have gone through all the nomenclature in the last class, and we understand that how this nomenclature works, and we understand how this Windows area help in designing the various factor in core type and the cell type. And then we have started that how this single phase core type transformer can be designed. So when we started there, then we understand that EMF, first we calculate the EMF. So In this EMF, we gone through E is equal to 4.44 F IM T volt. From there, ET is come as a it is equal to E upon T, and that's come as a 4.4 uh, FIM volts. Then we get the window in single phase transformer. Uh, so window in the single phase transformer contain one primary and the one secondary winding. Means only one type of the winding we require. So the window factor we calculate how this window space factor KW we can calculate and find out how much area we required on the window. As we understand, suppose we're talking about the code type. So this is our total window, or the area that we have to accumulate the this two binding of the this type and this type. So how much area we require that we go through this. So the window space KW is the ratio of the construction area in the window to the total area of the window. So KW will be the conducted area into the window divided by total area of the window. And this can be from here the conducted area of the window can be given as a KW multiplied with AW. And the current density will become as a delta is equal to IP upon AB, and it will become as IS upon AS. So the area of the cross section of the primary conductor AP will become as IP upon delta, and the area of the cross section of the secondary conductor will come AS is equal to IS upon the delta. So if we neglect the magnetizing EMF, then primary ampere turn is equal to the secondary ampere turns, and therefore we can from here we can calculate AP. It is will be equivalent to IPTP, and that will be equivalent to ISTS. So total copper area in the window can be total copper area of the primary banding plus the copper area of the secondary banding. So to calculate the copper area, what you have to do, you have to calculate the how many numbers of turns is there, means how much wire we require, and how much cross section area of that wire, कि हमको कितने वायर की जरूरत है और उस वायर का क्रॉस सेक्शन एरिया क्या है. क्रॉस सेक्शन एरिया का मीन्स यदि सपोज एक तार है, एक पतला सा हम लोग तार लिए, तो उसका क्रॉस सेक्शन एरिया कितना है, जो उसकी मोटाई कितनी है, डेट विल बी कम एज ए क्रॉस सेक्शन एरिया ऑफ द डेट कंडक्टर. So finally it is going to become as number of primary turns multiplied with area of the cross section of the primary conductor plus number of secondary turns multiplied with the area of the cross section of the secondary conductors. That will give you the total कॉपर एरिया. मीन्स इतना कॉपर हमको एक ट्रांसफार्मर को बनाने में लगने वाला है. ये इस बात से हम लोग डिसाइड करेंगे कि हमको कितने कॉपर टर्न्स चाहिए और उसकी क्रॉस सेक्शन एरिया हमारी तार की मोटाई कितनी है, एंड दैट विल डिसाइड द total copper area into the window. So we can calculate it from here. So it will become as a TP multiplied with AP plus TS multiplied with AS. These two means primary side plus secondary side. So finally it is going to become as TP means number of turns into the primary side multiplied with the IP by delta plus TS multiplied with IS by delta. So 1 upon delta will be get common, so it will become as a TPIP plus TSIS, and again it will become as a 1 upon delta AT plus AT as IPTP is equal to IS TS. So finally it is going to become as 280 divided by the delta. So one equation on the above equation, on equating this above equation, we are going to get as KWAW, and that will be it is going to become as 2 multiplied with 30 divided by the delta. This is the total equation that is going to become. So 280 divided by the delta. And from here we get the ampere turns, and it will be this ampere turns will become as 1 upon 2 AW multiplied with this delta. So from here we can calculate the ampere turns. What should be the ampere turns in the system? So the kVA rating of the single phase transformer, now it will be given as a kVA rating. So this is basically VPIP multiplied with 10 power minus 3, because suppose rating is given into the in volt, so we have to convert this into the kVA. So to convert this into kVA, we have to divide it by the 10 power, means divide. We need to divide it by the 1000, and that is going to become as a 10 power minus 3. So we going to the do it as a kVA rating is going to become as EPIP multiplied by 10 power minus 3, and it will be equivalent to the EPIP multiplied with the 10 power minus 3, and we assuming that there will be no loss, means जितना EMF हमारा ट्रांसफार्मर में जनरेट हो रहा है, जो उसका टर्मिनल वोल्टेज है और हमारा जो ईएमएफ जनरेट हो रहा है, दैट विल बी रिमेन्स इक्वल, बिकॉज जितना हम लोग सप्लाई करते हैं ट्रांसफार्मर को, और जो प्राइमरी साइड ईएमएफ जनरेट होता है, दिस इज बेसिकली नॉट इक्वल. इक्वल क्यों नहीं होता है? बिकॉज हमें डिफरेंट टाइप ऑफ द लॉसेस का सामना करना पड़ता है, लाइक कॉपर लॉस, ईडी लॉस, ऑल दिस थिंग्स. सो ईडी लॉस बेसिकली हमारा जो होता है वो मोस्ट ऑफ द टाइम डिपेंड्स ऑन द फ्रीक्वेंसी ऑफ द सप्लाई एंड what type of the material we are using. These are the two major factors which decide to the system. So ED loss in transformer is the amount of the heat caused by the its magnetic flux. How this magnetic flux is going to be circulated around the our conducting core. So this current circulate particularly to the flux, and this is going to give our spark. So these ED loss is happening due to the magnetic field, and most of the time it will be represented by the in terms of the its how much material is thick, how much its frequency, and what will be the its flux, and what will be its flux density. These things will decide its ED loss. So if frequency is uh, increased, then ED loss will be very high, because this is basically is proportional to the square of the frequency. So we just make sure that material should have the higher flux density, means उसका जो flux density है या जो उसमें जो flux linkage है वो थोड़ा अच्छा रहे. So these are the things that eddy current loss happen. We have another loss like copper loss is there, which is the ice for losses is there. So harmonics losses is there. So these things are going to affect the performance of the system, and due to this, the EMF which is generated is not equivalent to the amount of the voltage which is applied from the system. But as we assume that this is a single phase transformer, so single phase transformer, these losses will be very less, CD current losses and copper losses. So that's why and in static losses, these current, we are assuming that these three losses will be less. So you will see that eddy current loss and hysteresis loss is dependent upon the frequency, and copper loss is totally depends upon the amount of the current which will flow through the our turn. So now we have assumed that this will be that whatever the EMF will be generated, that will be around the same. So if it is the same, then we replace Dp by the Ep, and in this system we have just multiplied with and divided by the Tp, means the primary side turn number of turn. So if you do this, then Ep upon Tp is give you the EMF induced by the each term, means हर एक term में कितना EMF induce होगा, that will be given like by the Et, and AT will be number of ampere turns will be become the TPIP. So that equation, the KV rating now can be given in terms of the ET multiplied with AT and multiplied with the 10 power minus 3. Means ET तो रहेगा ही, साथ में 10 power minus 3 as constant. So it will become ET 18. So on substituting E and AT from the equation, we already get. Already we have a value of ET, which is a 4.4 F IM, and it is equal to 1 upon 2 kWAW delta. Now we put this value in this equation. So now our this KV rating, now it will become as a 4.44 pi F pi m, and the value of AT, which is a kWAW delta divided by 2 multiplied with 10 power minus 3. Now it's became the whole situation. Now these two will divide to this, so for it will become 2.22 I FIM, which is a kWAW delta, multiply with 10 power minus 3. Now we change this FIM, this flux with the flux density with the flux and ampere turns. So that will become as a 2.22 FBM AI kWAW delta multiplied by 10 power minus 3. So the above equation is the output equation of the single port type the transformer. So these calculation we have done for the single port transformer. Now how we can design the cell type transformer. यदि हमको सेल टाइप ट्रांसफार्मर को डिजाइन करना है तो वो कैसे हम लोग डिजाइन करेंगे. So the cell type transformer will be designed like this. Again, we write down E is equal to 4.44 phi m T volt. That is that will be remain same because EMF induced in the transformer is not going to be get differentiated. That will be remain same. ET will be given as ET is equal to E upon T. So that will become 4.4 F phi m volt. That will be the now value of the ampere per turns. So the window in single phase transformer contain only primary and secondary winding. So from here we can find out what will be the window space. So now let's calculate what will the window space. So total area of a window KW can be given as a conductor area into the window divided by total area of the window. तो हमारा टोटल एरिया विंडो विंडो कितना है. दिस इज आवर सपोज दिस इज आवर टोटल एरिया, दिस एरिया एंड दिस एरिया. ये हमारा टोटल एरिया है, इसमें कितना हमारा कंडक्टर पार्टिसिपेट कर रहा है, तो उतना बात को हम निकाल देंगे तो डेट विल गिव अस द डिवाइड करने पे ये हमको एक फैक्टर देगा, विंडो स्पेस फैक्टर. यदि टोटल एरिया को कवर कर देगा तो के डब्ल्यू विल बिकम 1. यदि कुछ एरिया को कवर करता कुछ एरिया कवर नहीं करता तो दिस विल बी नॉट 1, दिस विल बी द लेस देन 1. So in this way how we can able to calculate the KW. So now let's understand what will the value of KW. So the value of KW will be given as a conductor area and window divided by total area of the window. and finally it is going to become HAC divided by the AW. And the conductor area in the window is going to become AC is equal to KW divided multiply with AW, and the current density in the same in the both band will be given as delta is equal to IP divided by AP, and that will be also IS upon AS. So how much current will flow from the any binding, that will become IP upon AP and IS upon AS. These are the two another important thing. So area of the X section. So now we define this into the two sections. The area of the X section of the primary conductor AP will be given as a IP upon delta, and area of the X section of the secondary conductor AS will be given as IS upon delta. These are the two factors that we have. So if we neglect the magnetizing EMF, then primary ampere turns is equal to the secondary ampere turns. So if we neglect to both, then in that case, this is going to become like this. So if you neglect the magnetizing EMF, then primary ampere turns is equal to the secondary ampere turns. So therefore, again we can have the AT is equal to IP TP or IS TS. These are the two things that we will have. So as we have two windows, now you can see this is our Windows 1 and this is our Windows 2. These are the two windows we have. So it is sufficient to design one of the two windows as both the windows are symmetrical. And since the LV and SB are placed on the center leg, so each window accommodates the TP and TS number of turns primary and secondary battery. So we are going to engage with the this one, this primary this center leg we are going to use. So we can define this one means we can design for this one, and the same design can be used for the this one as well. मीन्स सपोज इफ यू डिजाइन दिस वन, इसको यदि हम लोग डिजाइन कर लेते हैं इस एरिया के लिए, तो जितना इस एरिया के लिए रहेगा सेम डिजाइनिंग हम उस एरिया के लिए भी कर देंगे। तो हमको दो बार कैलकुलेशन नहीं करनी पड़ेगी, सिर्फ इसका क्या है जितना इसको डिजाइन करना है तो उसका हमको डबल मीन्स आधे सिस्टम के लिए हम लोग डिजाइन करेंगे और आधे इस क्या कहते हैं आधे अपने केबी रेटिंग के लिए डिजाइन करेंगे और फिर हम लोग इसको डबल कर देंगे तो हमारा टोटल सिस्टम का आ जाएगा। So we follow to this one. So how we can follow to this one? So again we have to go to the from the beginning, मीन्स हमको कितना एम्पियर टर्न्स चाहिए कितना नहीं चाहिए ये हमको अब देखना पड़ेगा। तो उसको देखने का तरीका क्या है कि if you neglect magnetizing EMF, then primary ampere turns is equal to the secondary ampere turns. Means जितना इधर ampere turns रहेगा उतना उधर भी ampere turns रहेगा. So therefore this will become as AT is equal to IPTP and equal to ISTS. So since there are two windows, so it is sufficient to design one of the two window as both the window as a symmetrical. So since the LB and HB binding are placed into the center tag, each accommodates the TP and TS number of both primary and secondary binding. Means इसमें कोई अंतर नहीं होगा, दोनों समान नंबर ऑफ लेग्स कंटेन करेंगे। तो कॉपर एरिया हम लोग को कैलकुलेट करना है कितना what will be the number of copper area that we are going to use. So to this we can calculate using the again we will multiply with the number of terms multiplied with the cross sectional area of the that system कि उस क्रॉस सेक्शनल एरिया कितना है तो दिस विल बी कम एज ए टीपीएपी मींस एरिया वन का नंबर ऑफ टर्न्स मल्टीप्लाई विथ एपी plus TSAS. These two things will be given. So now we are calculate again. So AP can be given as a IP divided by the delta means कितना करंट डेंसिटी है और कितना करंट फ्लो कर रहा है उससे हमको क्रॉस सेक्शनल एरिया मिल जाएगा and we also get the IS divided by the delta. So this will give you the area of the second one. So we just replace AP and AS with IP and delta. So finally it will be going to come as a, if you see, then it is going to become like 1 upon delta AT plus AT. Means TPIP and TSIS is same. So in place of this, we will write down AT and AT, and it is going to become as AT 280 divided by the delta. And if you equate to this the above equation by using the when we calculating the total window, its conductor area in the window, how much conductor area in the window we will require. So this is KWAW is given, where KW means KW is the ratio and AW is the total window of the EP. So from here, I will replace to this. So the total amount of the area means already we calculated the copper area C, and then to calculate to this. This then this KWAW will become as 280 upon the delta. So how much copper area we require that we have calculated as KWAW, and we calculated uh, using the number of turns and number of ampere turns of the system. So from that we are going to get it as a 280 divided by the delta, and from here this 80 will become as 1 upon 2 kWAW delta. This is the amount of the ampere turns will come. अब हमको एम्पियर टर्न्स के बारे में पता चल गया कि एम्पियर टर्न्स हमारा कितना रहेगा एंड ये आ रहा है 1/2 kWAW डेल्टा. नाउ अब हमको पता करना है कि केवी रेटिंग कैसे डिसाइड करेंगे. सो टू डिसाइड द केवी रेटिंग अब हम क्या करेंगे, द केवी रेटिंग ऑफ द सिंगल फेज ट्रांसफार्मर टाइप अगेन इट विल बी गिवन एज Q इक्वल टू TPIP multiplied with 10 power minus 3. तो केवी रेटिंग क्या होता है, आइदर वी कैन डू इट फ्रॉम द प्राइमरी साइड और सेकेंडरी साइड. दोनों साइड क्या है, इसकी रेटिंग जो रहती है वो क्या रहती है, बराबर रहती है. हमारी जो पावर की वैल्यू है या तो प्राइमरी साइड या सेकेंडरी साइड दोनों बराबर रहती है ट्रांसफार्मर में. तो यदि हम लोग प्राइमरी वाइंडिंग को लेकर कैलकुलेट करें केवी रेटिंग या सेकेंडरी वाइंडिंग को लेकर कैलकुलेट करें केवी रेटिंग, दैट विल बी रिमेन सेम. तो केवी रेटिंग के विल बी गिवन एज VPIP 10 पावर माइनस 3 और यहाँ से आएगा हमारा EPIP 10 पावर माइनस 3. दिस विल द टोटल वैल्यू ऑफ द दिस डेल्टा, या जो भी वैल्यू है जो केवी रेटिंग है दैट विल बी गिवन एज VPIP और 10 पावर माइनस 3 एज हम लोग सिंगल फेज जनरल ट्रांसफार्मर को वोल्टेज में रेटिंग देंगे तो उसको केवी रेटिंग में कन्वर्ट करने के लिए यहाँ पे हम लोग 10 पावर माइनस 3 से डिवाइड कर देंगे इसको. or if you divide to this, or in again we equate this as a VP as a equivalent to EP. तो यदि हम लोग इसको कहे कि ये बराबर होगा, यदि बराबर होगा तो अब हम लोग इसको लिख सकते हैं ईपी ईपीआईपी 10 अब अगेन हम लोग दोनों साइड टी मीन्स दोनों में टीपी से मल्टीप्लाई और उसको डिवाइड कर दिए, यहाँ पे टीपी से मल्टीप्लाई किए और टीपी से डिवाइड कर दिए, तो इफ ईपी अपॉन टीपी विल गिव यू द ईटी ampere EMF generated per turns. This value gives you the EMF generated per turns, and this value TPIP will give you the ampere turns. So multiply with the number of turns, multiply with the primary winding, primary side current. So this will give you the 80. So finally it is going to become 80 multiplied by 10 power minus 3. So on substituting of E and 80 from the equation, now we are going to get Q is equal to 4.25, 4.44, the value of 80, 5 F phi m, or value of 80 is kWAW delta upon 2 divided by 10 power minus 3 as usual. Now we change Bm is equal to phi m divided by Ai. So this will become 2 upon 2 point. This is get divided by 2, so it will become 2.22 F phi m kWAW delta divided multiplied with 10 power minus 3, and finally it is going to come 2.23 F Bm Ai kWAW delta multiplied with 10 power minus 3. So the above equation is the output equation for cell type of the system. यदि सेल टाइप हमको डिजाइन करना है तो उसका इक्वेशन है, और यदि हमको कोर टाइप डिजाइन करना है, कोर टाइप डिजाइन करना है तो उसका इक्वेशन, दिस इज आवर इक्वेशन, और दिस इज आवर सेल टाइप इक्वेशन. नाउ वी हैव गॉट द इक्वेशन. हमें पता है कि यदि रेटिंग हमको यदि पता चल जाए कितने रेटिंग का हमको डिजाइन करना है, फिर हमको मटेरियल पता चल जाए कि उसका मैग्नेटिक फ्लक्स कितना होगा, हमको एक विंडोज हम लोग फिर उसके हिसाब से करेंगे कि कितना विंडोज हमको रिक्वायर्ड है, कितना उसमें हमको कॉपर पिन डालना पड़ेगा. दिस ऑल थिंग्स विल बी हेल्पफुल इन डिजाइनिंग अ सिंगल फेज ट्रांसफार्मर. Similarly, we can design for the three-phase transformer as well. और three-phase में again we go for the firstly core type. So core type में अब three-phase transformer की जरूरत क्या है कि अब हमको 3 लिंक चाहिए, क्योंकि अब हम हमारा जो सिस्टम है क्या है, 3 फेज का रहेगा. तो घरों के अपने घरों के आसपास जो आप लोग ट्रांसफार्मर मोस्टली देखते हो क्या है, दिस इज अ टाइप ऑफ द 3 फेज ट्रांसफार्मर. और यदि वो 3 फेज ट्रांसफार्मर है तो दैट ट्रांसफार्मर विल रिक्वायर 3 फेज. और यदि वो 3 फेज बनाना है तो वी रिक्वायर द बिगर एरिया एज कंपेयर टू द सिंगल फेज. सिंगल फेज का मतलब हुआ किसी भी हमको एक ट्रांसफार्मर को ही डिजाइन करना पड़ेगा, एक फेज के लिए डिजाइन करना पड़ेगा. लेकिन 3 फेज का मतलब क्या हुआ कि अब हमको जो ट्रांसफार्मर है दैट नीड टू बी डिजाइन फॉर द 3 फेज. और 3 फेज के लिए हमको 3 डिफरेंट लेग्स भी चाहिए. So core type 3 phase transformer has 3 limbs and 2 window as shown in this figure. So each limb carry the low voltage and high voltage band of the phase. तो एक जो कोर है हमारा, एक कोर है गया तो इस पे एक फेज आ गया, एक दूसरा कोर है तो इस पे दूसरा फेज, और एक तीसरा कोर है तो इस पे तीसरा फेज. और ये दो हमारा क्या रहेगा, विंडो एरिया रहेगा, जहाँ पे हम लोग will decide how much area we require for the this. So this area, these things give you the number of area, number of turns, all these things will be come up from me. Again, we go for the simpler, similar design. First, we calculate what will the induced EMF. So this will be given by 4.44 at 5 T volt, and ampere per turns will become as it is equal to E upon T. So this will be given by the. So E will become as 4.44 pi mt volt, and ampere per turns will become it is equal to A upon T. So this is going to become 4.4 uh, F pi m volts. So how much EMF per turns can be calculated? That will be decided by the this. From this, it will be coming as a 4.4 pi F pi m. So in case of the three-phase transformer, each window has two primary winding and the secondary winding. So now in the single phase, we are having only the one primary winding and one secondary winding. But here we can see that this is going to be have the two winding, and you can see that we are going to have the this suppose this if you talk about this band this window, then we have a one single one low voltage and second low voltage. Similarly, one high voltage and second high voltage, and this window will also have the same one low voltage, another low voltage, and one high voltage and another high voltage. So now our job is a little bit became tedious. थोड़ा सा अब हमको परेशानी होगा कि कैसे अब हम टोटल एरिया निकालें और कैसे नंबर ऑफ टर्न्स निकालें. दैट्स द मोस्ट इम्पॉर्टेंट थिंग. सो सबसे पहले हम लोग विंडो स्पेस की बात करते हैं. तो इफ यू टॉक अबाउट द विंडो स्पेस, देन इट विल बिकम एज ए कंडक्टर एरिया एंड द विंडो डिवाइडेड बाय द टोटल एरिया ऑफ द विंडो. तो एक में जितना कंडक्टर है और दूसरा डिवाइडेड बाय द total area of the window. So this is come as AC upon AW. AC is equal to KW multiplied with AW, or फिर current density delta will be IP upon AP or IS upon AS. कि जो हमारा एरिया है कंडक्टर का और कितना हमारा उसमें से करंट फ्लो कर रहा है विल गिव यू द करंट डेंसिटी. और यहाँ से एपी एंड आईएस की क्रॉस सेक्शनल एरिया हम लोग निकाल सकते हैं. सो एरिया ऑफ द क्रॉस सेक्शन ऑफ प्राइमरी कंडक्टर एपी विल बी आईपी अपॉन डेल्टा, और आईएस का हमारा क्या हो जाएगा आईएस अपॉन डेल्टा. सो टाइम हैज बीन लिमिटेड फॉर टुडे. आज मैं यहीं पे स्टॉप करता हूँ. नेक्स्ट वीक हम नेक्स्ट क्लास में इसको कंटिन्यू करेंगे. So let me just check quickly your attendance. So today present are Abhishek Kumar Bhadoria, Adan Kumar Sami, Abhijit Roy, Ankur Kumar, Ashok Kumar Kewat, Giriraj Arya, Goyal, Meridun Khan, Najeez Ahmed, Pawan Kumar Khare, Pravesh Kumar Joshi, Rahul Pachori, Roshan Raj, Ravi Kumar, शैलेश कुमार पुचिया, शक्तिमान कुमार, सुशंकर कुमार, सुभानी शेख, सूरज कुमार मौर्य, सुशील कुमार, and Yogesh Kumar. Anyone in support in this? Okay, thank you everybody. We meet tomorrow and we continue with this.